In this video, I am going to explain improper rotation axis and center of symmetry. Let us first consider this one. We start with an example, the example of methane molecule. We know that the tetrahedral structure of methane can be drawn within a cube. For example, let us consider a cube like this. Consider a cube like this. The carbon atom is situated somewhere at the center of the cube, and hydrogen atoms are placed at alternate corners. Here, then this one is omitted, then this corner is omitted, this corner, and this one is omitted, this corner. These are the four positions of the hydrogen atoms in methane. These are the bonds, CH bonds. This is well known. Now, consider an axis of rotation like this, passing through the centers of the top and bottom faces. Call it AB. Clearly, this AB is a twofold rotation axis, because if we rotate through 180, this atom will come to this position and this one goes to this position. Similarly, 3 goes to 2 and 2 goes to 3. So AB is a twofold rotation axis. But if we rotate it through an angle of 90 degree about AB, what will happen? The overall shape of the cube does not change. The cube retains its shape, but the position of the hydrogen atoms will change. Carbon atom remains here. Now by 90 degree rotation, one comes here, because this angle is 90. This angle is 90. So one comes here, 4 goes to this position, two comes here. We are carrying out an anti-clockwise rotation. 1 comes to 4, 4 goes to 1. 2 comes to this position, and 3 goes to this position. This is now the configuration of the molecule. Clearly, this is an inverted configuration. These two are not the same. If we call it 1 and this one 2, then 1 and 2 are clearly not equivalent. Therefore, this 90 degree rotation is not a symmetry operation. Now carry out a reflection on this plane. Consider a plane like this, perpendicular to the line AB and placed in this manner, cutting the cube into 2 equal halves. If this is a plane of, this is not independently a plane of symmetry, but we imagine a mirror plane like this, perpendicular to AB. AB is here. If we carry out a reflection on this plane, what will happen? The cube, the upper portion of the cube will go to the lower portion, and this part will go to the top part. The overall cube retains its shape. The overall cube remains a cube, but but the arrangement of the atoms will change. 2 goes to this corner, so this is the new position of 2. 4 comes down to this corner, therefore this is the new position of 4. Carbon atom remains here. 3 goes up, 3 go from the bottom, 3 goes to the top by reflection on this plane. So 3 from here goes to this position, and 1 from here comes to down to this position. Now the configuration, the bond arrangements are like this, and we compare these two. They are now equivalent. If we don't look at the labels, then the two molecules are the same. So this configuration 3 is equivalent to 1. Therefore, this whole operation is a symmetry operation, because we know that all symmetry operations produce equivalent configurations. Therefore, the combined operation C4, this is a C4 operation followed by a perpendicular reflection operation, is a symmetry operation. Symmetry operation. We call it an improper rotation, 4-fold improper rotation operation. AB is called a 4-fold. AB is called a 4-fold improper axis of rotation. Improper axis of rotation, or an alternating, a 4-fold alternating axis of symmetry. This is also another name for improper axis. So this is one example. Let us consider another example. Consider benzene molecule, which we are very much familiar with this molecule, benzene. The carbon atoms are numbered in this manner. Now this is perpendicular to the plane of the paper. There is a C6 axis. This C6 axis independently exists. C6 is in fact a genuine rotation operation. Here this 90-degree rotation is not a symmetry operation for this molecule, but here C6 is a symmetry operation by itself for this molecule, and the resulting configuration is this. If we rotate anti-clockwise, then 1 will come here, 2 here, 3, 4, 5, 6. This will be the resulting configuration, and then if we reflect on a plane, the molecular plane itself is a plane of symmetry. This plane also exists independently. We call it for the time being sigma perpendicular. Then if we carry out this symmetry operation now, we will get this 6 bar. All atoms will remain in their own positions, but the associated atomic orbital lobes or vectors associated with the atoms will be inverted. We use a bar notation to indicate this. Now, this configuration is also equivalent to this one, because if we remove the labels, then the two structures are the same. So this is also a symmetry operation, and it is actually a combined operation, C6 operation followed by sigma perpendicular. We call this S6 operation. So this C6 axis also acts as an S6 axis, improper 6-fold axis. In this particular case, proper axis and improper axis coincide. By comparing these two, we arrive at a very important conclusion, that whenever a improper symmetry operation is possible, the associated rotation and reflection operations may or may not exist independently. In this case, they exist. In this case, they do not. We write this. If Sn exists, Sn means n-fold improper rotation. If Sn exists, the corresponding Cn and sigma plane, Cn as an axis, as a symmetry element, Cn and sigma plane as a symmetry element may or may not exist. Sometimes they exist, sometimes they do not. But the combined operation Sn is possible in many cases. Next, let us come to center of symmetry. Center of symmetry. Center of symmetry. This is also very easy. Consider the most familiar example, linear CO2 molecule. Consider a point here, start from oxygen atom, proceed to this point, and proceed further on the same direction, along the same line, up to an equal distance. Then from this oxygen, you will arrive at this one. So this point is called the center of symmetry. Similarly, for benzene, if you start from this hydrogen, walk up to this point, and then go straight along the same line up to an equal distance, you will arrive at another hydrogen atom. This is true for all H atoms, etc. Therefore, this point is the center of symmetry for this molecule. Here, this carbon atom, center of the carbon atom is the center of symmetry for this molecule. Such centers of symmetry are indicated by I, inversion center, I, and the associated operation is denoted as I with a hat. If you want to carry out I operation on this molecule, what do? We use labels 1, 2, and then after inversion we get 1 bar on the left and 2 bar on the right. Bar because if you have a vector here, say p orbital here like this, then that will be inverted. That will, on this side, after traveling in that manner, you will get an inverted vector. That is why we use bar notation in this case. Similarly, if you carry out inversion through this point, then the atom labels will carry bar notation. If it is 1, 2, and so on, these will be 1 bar, 2 bar, and so on. And clearly, I operation carried out 2 times will give you the identity operation, because inversion, then again inversion will bring you back to the original configuration. So, thus far we have obtained 5 elements of symmetry. Elements. What are they? They are identity element, then rotation, then reflection, then improper rotation, and center of symmetry. The associated operations are, symmetry operations are do nothing. This is denoted by this. Rotation is denoted by this with hat. Reflection is denoted by this. Sn operation is denoted by this. In textbooks, you will find that there is no distinction between the symbols for operation and symbols for the symmetry elements. But I prefer to use such symbols in order to avoid confusion. Symmetry elements and symmetry operations are different. They are geometrical entities and they are actions carried out with the help of those geometrical entities. So let me finish at this point now. I will discuss more elaborately in a next video. I thank you very much for watching this video. And